There are a lot of beautiful things in our world, but there's a special kind of beautiful for each of us. Euler's identity is one kind of beautiful. To appreciate its beauty, we have to have some background knowledge about several topics of math. Pi is simply the ratio of a circle's circumference to its diameter, and it's equal to approximately 3.14. E is a unique positive constant number that's approximately equal to 2.71828. This number is the basis for so many real-world applications involving exponential functions that the idea of how it came through is very interesting. One way to look at it is through the compound interest formula. In this equation, P is the principal invested at an annual interest rate R, which is in decimals, compounded n times a year. A is the balance in the account after t years. Let's say I invested $1 at 100% interest rate for 1 year, so both t and r are equal to 1. I'll get the following: a equals 1 plus 1 over n all to the power n. Now let's assume that this interest rate was compounded every month. Substitute 12 for n in our equation and you'll get a equals 2.613. If I compounded it every day, I'll get a to be 2.71456. Every minute, I'll get a equals 2.718279. What we notice is that as n increases, a, the balance in my account, keeps getting closer to the number e. So we can define the number e to be the number that the function f of n equals 1 plus 1 over n all to the power n approaches as n approaches infinity. Previously, when we were given the equation x squared equals minus 9, we found it has no real roots, which is why the imaginary number I came to be. The number n is a positive real number. If we multiply n by minus 1, we'll get minus n. We know that the absolute value of any real number is essentially the distance of that number from the origin on the number line, which means that absolute value of n equals n, and absolute value of minus n equals n. So basically, minus n is a reflection of n across the origin, which means that if we rotate n 180 degrees, we'll get minus n, the same result as multiplying n by minus 1. Instead of rotating 180 degrees, I could also rotate the number n through two intervals of 90 degrees each. Assuming a rotation of 90 degrees is equal to multiplying by x, if we rotate n twice to get a rotation of 180 degrees, we get x times x equal negative 1 or x squared equals negative 1. Take the square root of both sides to get the square root of negative 1, which means that a rotation of 90 degrees must be equal to multiplying by I, which is equal to the square root of negative 1. Let's stop here for a moment and consider complex numbers. A complex number has two parts, a real part and an imaginary part. It's expressed as z equals a plus b times I. Complex numbers can be graphed on the xy plane because the x and y axes are real number lines. We could solve this problem by multiplying the x-axis by I, which will rotate it 90 degrees and form the imaginary axis. This new system of graphing is called the complex plane. Using the Taylor series, the function e to the power x can be expanded and written as follows. We can also expand cosine theta and sine theta to the following. Now substitute I times theta for x to get e to the power I times theta, which we expand to get this. After isolating the terms multiplied by I and factoring I out, we get a familiar pattern that gives us the rule that e to the power I times theta equals cosine theta plus I times sine theta. To graph the complex number z, the real part of z goes on the real axis and the imaginary part of z goes on the imaginary axis. Z is represented as a position vector with its tip at coordinates a, b. The angle between z and the real axis is called the argument of the complex number, while r is the magnitude of z. We can calculate r using the Pythagorean theorem and the argument using simple trigonometric functions. Consider this: what if we have the argument of z and the magnitude r given, and we're asked to write them in the original form z equals a plus b times I? Simple, we could use trigonometric functions. Use cosine theta equals a over r to find a, and use sine theta equals b over r to find b. Now substitute a and b in the original form of z. When we factor out r and take it to be equal to 1, we get Euler's formula that we proved earlier. Substitute pi for theta in the equation. Sin pi is equal to 0, so the second portion of the equation cancels out, leaving us with just cosine pi, which is equal to negative 1. And that is Euler's identity, which can be rewritten as e to the power I times pi plus 1 equals 0. It's amazing to see how numbers that might as well be from other worlds combine in this identity along with the most famous operations and the identity elements of multiplication and addition to give the world's most beautiful equation.